alkynes. These are the compounds, organic compounds having carbon-carbon triple bond as the main functional group. Called as alkynes. And we know the general molecular formula of the alkynes is CnH2n minus 2, and the triple bonded carbon hybridization of triple bonded carbon is sp, bond angle 180 degrees, shape is linear. Now let us try to see the preparation of these alkynes. How to prepare these alkynes? So first of all, it is from the dehydrohalogenation of dihalides. Dehydrohalogenation of dihalides. So these dihalides may be vicinal dihalides or gem dihalides. Vicinal dihalides means halogen atoms are present on the adjacent carbon atoms, and geminal means the same carbon atom. So let us take vicinal dihalides initially. So I will take this molecule, simple molecule. The name of this molecule is, at first position and second position bromine atoms are there. So it is called as 1,2 dibromoethane. So when it is subjected to the alcoholic KOH, alcoholic KOH is a dehydrohalogenating agent which eliminates one hydrogen and halogen from the adjacent carbon atoms, so that it makes a double bond between the carbon atoms from where these two atoms are being removed. So we can write the molecule like this. So we got this molecule after the removal of the hydrogen halide. This is called as the vinyl bromide, and this is not the alkyne, it is an alkene part with halogen. Now to get the alkyne, you need to remove one more hydrogen and bromine, so that one more bond will come between these two carbon atoms. And for that purpose, we cannot use the alcoholic KOH. Why? Because the strength of the alcoholic KOH is not enough to remove the hydrogen and halogen from the unsaturated compound. The reason is, bromine is having the lone pair of electrons. These lone pair of electrons are in conjugation with the pi bond of the carbon-carbon double bond. So because of that, this carbon halogen atom gets the double bond nature, for which this OH minus ion cannot remove the bromide ion. So that is the reason why what we do is, we use the strong dehydrohalogenating agent, that is sodamide, NaNH2. So when sodamide is used, this sodamide has the sufficient ability to remove the hydrogen and halogen even from the unsaturated compounds, so that hydrogen halide will be removed, and finally we get the hydrogen C triple bond CH. This is the acetylene molecule. Okay. So here you can do one thing, that not necessary to use the alcoholic KOH, even you can use the directly sodamide in both the cases. Let's try to see one more molecule. one more example. A general dihalide, let us try to take. Plus now we are using the 2 moles of sodamide directly. So in first step 1 mole of HBr will be removed, and in the second step second HBr will be removed, and a triple bond means 2 bonds will come in addition to this existed bond, so that we get the triple bond between these 2 carbon atoms. Okay, so this is the way to get the alkynes from the dihalogen compounds. Now let us see a small conversion, how to convert the alkene molecules to the alkyne molecules. Just I will take the note here. So by this particular method, we can convert alkene to alkyne. You must remember that now I am introducing this slowly conversions. After this lesson, there are a lot of conversions. This is the starting conversion part. So I will take an example here. You just take the CH2 double bond to CH2. This is ethene molecule. So this ethene molecule I would like to convert into the acetylene molecule, that is CH triple bond CH. This is ethene and this one is ethyne. So what are the steps and what are the reagents to be used? It is very simple that here initially you take the ethylene molecule and subject it with the bromine in the presence of the CCl4, carbon tetrachloride. So bromine will be added to the both of these double bonded carbon atoms, so that we get the CH2 Br and CH2 Br. The molecule is like this. Now use the 2 moles of NaNH2, because each mole removes 1 hydrogen halogen. So out of these 2 hydrogens, we write down 1 hydrogen here. So hydrogen halide, and here also hydrogen halide. So finally we get the CH triple bond CH. So in this way we can convert the alkene molecule to the alkyne molecule. Now let's try to see how to prepare the alkynes from the tetrahaloalkane molecules. Second step is by heating 1, 1, 2, 2 tetrahaloethane molecule. This means I am preparing the ethane molecule, means acetylene molecule. So here only halogens will be removed. So this process is called as the dehalogenation. Okay. So in this dehalogenation process, you just take CHCl2. I will take another color. CHCl2, single bond CHCl2. So 1, 1, 2, 2 tetrachloroethane. So just treat with the 2 moles of the zinc in the presence of the alcohol and heat it. So this zinc will take the each zinc will take the 2 halogens, so that 2 moles of the zinc will take the 4 halogen atoms and develops a triple bond, means double bond, 2 more bonds in addition to the single bond, existed single bond, so that we get the ethane molecule plus ZnCl2. So this method is useful for the purification of the ethane, and higher alkanes also prepared here. You just see one more general example I will take here only. RCX, some halogens, hydrogen, 2 moles of the zinc, add alcohol and heat it, just remove these halogens and put two bonds in addition to this existed single bond between those two carbon atoms so that we get the ethyne molecule. So this is the second method. And third method is from chloroform or iodoform simply, means haloform. So it is by heating iodoform with silver. So just take the iodoform. Iodoform molecular formula is CHI3. So you take the 2 moles of the iodoform. I'll write the CHI3 like this. And to this you add this silver. We know that each silver combines with only one halogen. Here 3, here 3, totally 6 halogens are there, so that you need to add 6 moles of this silver and just heat it. So each silver will take off these halogen atoms, so that these two carbons which are losing these halogen atoms will be connected through triple bond, and finally 6 moles of AgI will be eliminated and we get the ethyne molecule. And step 4 is electrolysis, again coal based electrolysis. So in the coal based electrolysis, we will take the potassium fumarate. CH, COOK, double bond CH, COOK. So when this molecule is subjected to the electrolysis and there is a loss of the carbon dioxide molecules as well as development of the bond between these two existed double bonds, so that we get the triple bond. CH triple bond CH plus 2 CO2 plus 2 KOH plus H2. Okay. So in this way we can prepare the acetylene molecule. Now let us see the laboratory method, how to prepare the alkyne, means acetylene, with the laboratory. So laboratory method. So in this laboratory method, we just take the calcium carbide, CaC2, calcium carbide, on reaction with the water, it produces C2H2, that means CH triple bond CH plus calcium hydroxide. Since calcium carbide is able to give the acetylene, this calcium carbide is also called as the acetylide. So they may ask the question, which of the following compound is an acetylide? It is nothing but the calcium carbide. But the disadvantage of this reaction is, whenever you are preparing the acetylene using the calcium carbide, you will get this some compounds as impurities, that is such as phosphine, PH3 may exist as the impurity, and hydrogen sulfide, arsine, ammonia, these all molecules actually present as impurities. So that is the reason how to remove these impurities and to get the pure acetylene molecule. It is simple thing that the moment when calcium carbide is subjected to the water, we get the acetylene and all these impurities. So all these products we will allow to pass over the copper sulfate solution, like this. So when we allow these gases to pass over the copper sulfate solution, hydrogen sulfide reacts with the copper sulfate and forms the copper sulfide, which is a black PPT. It precipitates out and forms the sulfuric acid. Similarly, phosphine combines with the copper sulfate and forms the Cu3PO2, copper phosphide, cupric phosphide. It is also a black PPT. cupric phosphide plus it forms the H2SO4. Just I did not balance this equation. So in this case you need to take the 3 moles of the copper sulfate and 2 moles of the phosphorus, so that here we get the 3 moles of the sulfuric acid. So in this way we get the pure acetylene gas. And you must remember that while preparing these acetylene gases, there must not be any fire. There must not be any fire in the vicinity of this reaction, means nearby this reaction there should not be any fire. The reason is acetylene easily catches the fire. It easily catches the fire and it undergoes combustion reaction, finally gives the carbon dioxide plus water and releases enormous amount of the heat energy. So that is the reason why this particular acetylene is used in the gas welding. So the gas present in the gas welding is acetylene gas. Okay. Now, apart from this calcium carbide, there is one more metallic carbide which is used in the preparation of the alkynes, not acetylene. That is magnesium carbide, Mg2C3. So when magnesium carbide is subjected to the hydrolysis, so magnesium carbide here 3 carbon atoms are there, so that you get the alkyne with 3 carbon atoms, that is propyne molecule you will get. Propyne molecule plus remaining is simply magnesium hydroxide. Okay. So since magnesium carbide is able to provide the propyne, it is called as the propynide. It is also called as the propynide, and the reaction, this reaction is also known as the Berthollet reaction. Now, let us see some of the physical properties of this acetylene. Physical properties of acetylene. So, first of all, C2H2, what we are calling as acetylene, is a gas. Actually, it is a colorless gas. We must add that point also. Colorless gas, and it has no odor. It has no odor. But in some textbooks they give it has garlic odor. So garlic odor, even in conversion reaction they used to mention the following: there is a unsaturated gas which has the garlic odor, reacts with the so-so and compounds and giving this product. So they mention it is a garlic odor, but a pure acetylene do not have any odor, and it only impure acetylene is having the garlic odor. The garlic odor of this impure acetylene gas is due to the presence of the phosphine gas. That's why it has the garlic odor. Actually, original gas do not have any garlic odor. And second point is, it is insoluble in the water. Insoluble in water, but highly soluble in acetone and alcohol. Okay. Actually, acetone, this acetylene gas is transported at the highest pressures using the acetone as the main liquid, where acetylene gas is properly soluble in acetone. And now let us see some of other physical properties. Since in alkynes, each triple bonded carbon atom is undergoing the sp hybridization. Most of the alkynes are having the acidic nature. And we must understand one more thing, that do all alkynes are having the acidic nature, or only few alkynes are having acidic nature? You must remember that the alkynes having triple bond CH are acidic in nature, and alkynes which are not having that group but having this type of the group are not acidic in nature. And the alkynes in which triple bond CH is present are also called as the terminal alkynes. Terminal means triple bond is present at the end of the alkyne, end of the molecule. And if a triple bond is present other than at the terminal position, are called as the internal alkynes. So only internal alkynes are not acidic in nature, only terminal alkynes are acidic in nature. Let us see why the terminal alkynes are acidic in nature, why not it is possible in the case of the internal alkynes. If you see terminal alkyne, the terminal alkyne molecular structure will be like this, and an internal alkyne structure will be like this. Okay. So to show the acidic nature, the molecule must be able to release the H plus ion. So here all these triple bonded carbon atoms, though they are sp hybridized, sp hybridized means more electronegative in nature. So because of highest electronegativity, this carbon hydrogen bond becomes polar, and carbon withdraw the electrons from the hydrogen so that it can immediately release the H plus ion and forms alkynide. It is called as alkynide. Okay. And in this case, this molecule is not able to release the H plus ion even though sp hybridized carbon atom is there, because there is no hydrogen. That's why these molecules are not acidic in nature, and terminal alkynes are acidic in nature. Now let us compare the acidic nature of these alkynes with some other compounds. The acidic nature of these compounds like water and alcohol, if you take, so I will write down their order, it may be very helpful to you. Acidic nature. So acidic nature of the molecules is water has the more acidic nature than the alcohol, which has the more acidic nature than the alkyne, means acetylene here, which has the more acidic nature than the ammonia, and which has more acidic nature than even normal alkenes, that means RH. And the question arises usually among the students that here oxygen hybridization is sp3. Here also oxygen hybridization is sp3. Carbon hybridization in both the cases is sp hybridized. Nitrogen hybridization is sp3. Carbon hybridization is also sp3. Usually we say that the electronegativity of the sp carbon is more than the sp2 carbon, which is more than the sp3 carbon. So first of all, let us discuss this point, then we shall come to this particular point. So I will take this space this side. So whenever we come to the point, if you take 3 molecules of this category, that means acetylene, ethene and some ethane molecule. Here the carbon atoms undergoes sp hybridization, sp2 hybridization here, and here it is sp3 hybridization. So now we know that electronegativity of the sp hybridized carbon atom is more. So that these are more acidic in nature, means alkanes are more acidic in nature than the alkenes. Alkenes are little bit more acidic in nature than the alkanes. So this is possible only when all the carbon atoms of all these molecules are having the only carbon atom. See here acetylene, ethane, ethene and ethane molecule, there is only carbon atom, and we are comparing the hybridization and electronegativity of the only carbon atoms, not with the other molecules. But in this particular case, oxygen is there. Oxygen is more electronegative than the carbon. So even though here it is sp hybridized, but oxygen electronegativity predominates over the sp hybridized carbon atom, electronegativity of the sp hybridized carbon atom, so that oxygen can easily withdraw the electrons from the oxygen hydrogen bond, so that it can release the hydrogen readily than remaining compounds. So if you take the water molecule, the structure is like this, 1 minute, and alcohol, it is like this. So when you compare here, oxygen is more electronegative when compared to the hydrogen, withdraw the electrons, so that get the partial negative charge, and hydrogen is the partial positive charge. Okay, but in this case, though here only one bond is there, that is more polar, that is here partial negative charge, partial positive charge will be there, but here carbon part, what is present, it releases the electrons towards the oxygen, so that the density of the negative charge will be reduced by the donation of the electrons from the alkyl part. Hence, oxygen cannot withdraw the electrons from the hydrogen single bond like in the case of the water. So that here oxygen can easily withdraw the electrons and release the H plus ions, so act as the strong acid. But in this case, oxygen cannot release the hydrogen because it is no longer have the same type of the electron deficiency like in the case of the water. So water is more acidic nature than the alcohol, first of all, clarification. And when compared to this nitrogen CH4 molecules, nitrogen pair of electrons are there, so it can easily donate the pair of electrons. So moreover, it is a base actually compared to the acid. Okay, so that is the reason why here there is no such type of the electrons to donate, only pi electrons are there. So lone pair of electrons can easily be donated compared to the pi electrons. Why? Because pi electrons are bonded electrons and they are connected to the nuclei of the two of the bonded atoms, but here lone pair of electrons are connected only, attracted to only one nuclei. So that's why acetylene is more acidic in nature than the ammonia. When compared to the carbon and means methane and ammonia, nitrogen is more electronegative than the carbon. So withdrawing capacity of the nitrogen of the hydrogen electrons is more compared to the methane. So that is the reason why ammonia is strong acid than methane molecule. And their relative basities, basic nature of their respective anions will be like this, opposite nature. So OH minus is weak base compared to the RO minus. I am writing the basicity. You must carefully observe this basicity. It is helpful in writing the reactions mechanisms also. Alkoxide is strong base than the alcohol. So whenever you are using the alkoxide part, it eliminates the hydrogen more effectively than the like NaOH, whatever you are using hydroxide parts, is weak base than the alkynide. I am taking only one negative charge, you can take both the negative charges. Is weak base than NH2 minus. Now I think you understood now. We have used NaNH2. NaNH2 dissociates into Na plus plus NH2 minus. Since it is a strong base, is able to replace the hydrogens even from the alkene parts. Even this is a weak base than the CH3 minus. So weaker the acid, strong will be its base. So basicity order is like this, acidic order is like this. You must remember this one because this order is usually helpful in writing the reactions, and most of the time this order has been asked in the examinations. So now let's try to write down, let's try to prove the acidic nature of the acetylene molecule, how it acts as acidic nature and how to understand its acidic nature. Very simple, certain reactions are there. So whenever you take acetylene molecule, this is ethyne, I am writing the UPSC name over here. So when ethyne is subjected with the sodium liquid ammonia, sodium in the presence of liquid ammonia. Sodium is a metal. Metal generally when react with the acid, it liberates the hydrogen gas. So from where it can remove the hydrogen? This place and this place. So since only one sodium is used, imagine only one hydrogen has been removed. So I am writing that CH triple bond C minus Na plus. This is called as monosodium acetylide. Single sodium is there, no? Since it is called as monosodium acetylide. So this monosodium acetylide means here there is a loss of hydrogen, half hydrogen gas. 2 cancel out, only one hydrogen it shows. Okay. This when subjected with another mole of the sodium in the presence of again liquid ammonia, means you can use 2 moles of sodium at a time here. Just I am taking this step by step. Now this sodium is able to release the one more hydrogen that is present over here, so that we get the ion like this. This is an ionic compound, not the covalent compound. The bond between the 2 carbon atoms is covalent, but the bond between the carbon and sodium is ionic in nature. So this is called the disodium acetylide. Okay, plus half hydrogen gas. Then what is the use of this particular reaction? So by this reaction, it is very clear that we have proved that alkynes, terminal alkynes are acidic in nature. Why? Because they react with the metal and liberates the hydrogen gas. So not only this particular molecule, even you can take the another molecule like this is a terminal alkyne. So terminal alkyne when subject with the sodium liquid ammonia, so that sodium replaces this hydrogen, so that there may be liberation of half mole of the hydrogen gas, so that we get this particular molecule. Then how to name this molecule? Because alkyl part is there, so it is called as the monosodium. Simply sodium we can write, because there is no other sodium is not possible. Even though let us write down monosodium alkynide, not acetylide. Since it is from acetylene, I have written acetylide. It is simply alkyne, so that I have written the alkynide. So like this molecules are formed. Now let us take another alkyne part. This is simply alkyne. So this alkyne also again you take the sodium liquid ammonia. No reaction happens because there is no replaceable hydrogen. Only alkyl groups are there which cannot be removed. Okay. Then what is the use of this reaction? Actually this reaction is helpful in separating the terminal alkynes from the internal alkynes. Terminal alkynes react with the sodium and liberates the hydrogen gas, whereas internal alkyne do not react with the sodium in the presence of the liquid ammonia. So by this reaction we will be able to identify which is the terminal alkyne, means in which compound there is a triple bond CH, and internal alkyne. And there is another use of this reaction. So from this particular alkynides we will be able to form the higher alkynes. I will show you how to prepare the higher alkynes with this monosodium or disodium alkynides. So preparation of higher alkynes from acetylene or terminal alkyne. So you see here, I will take both of these terminal as well as the acetylene molecule. So initially I will take the acetylene molecule CH triple bond CH and subject it with the sodium, just like we did in the earlier reaction, and liquid ammonia and loss of hydrogen gas. So we get the monosodium acetylide. This monosodium acetylide when subjected with the alkyl halide. Any alkyl halide you can take here. I'll tell you how to take alkyl halides also later. Let us take the alkyl halide. So in the alkyl halide, there is halogen that gets the partial negative charge and alkyl part will get the partially positive charge. The reason is halogen atom is more electronegative than the alkyl part, so it becomes a polar bond. So here this particular negative charge attacks over the alkyl part and replaces the halogen as X minus. This X minus combines with the sodium ion to form NaX, sodium halide. Afterwards, we get the CH triple bond C alkyl part this side. Still one more hydrogen is there. So again, you will be able to make this particular molecule react with the sodium in the presence of the liquid ammonia. So there will be loss of again half mole of the hydrogen gas, and we get now sodium alkynide now. This sodium alkynide, again when you subject with the another alkyl halide, this negative charge again attack over the alkyl part, replaces the halogen, so that there will be loss of sodium halide, means it will be eliminated as a byproduct, and now we will get the R dash C triple bond C R. Actually, we have started with a molecule with 2 carbon atoms, and we have prepared the higher alkyne, means having the more number of carbon atoms. Now, if we take, what happens if you take the CH3Cl? I will take the 2 different molecules here just to see. So, I am writing all these reagents at a time: sodium, liquid ammonia. So, we will get this particular step, and second I am writing CH3Br, means this one, alkyl halide. So, this particular carbon will attack over this methyl group and removes this bromine. So, we get the CH triple bond C CH3. And next one, and first step here, again we are using the sodium, liquid ammonia, and second one we are using the CH3 CH2Br, ethyl bromide. Now, this side you will get the ethyl group. So, the molecule will be CH3 CH2 C triple bond C CH3. So, this particular alkyl part is different from this particular alkyl part. So, it depends on what type of molecule you want to prepare. If you want to prepare 2-butane, 2-butane means the molecule will be like this: CH3 C triple bond C CH3 from this particular alkyne. In such cases, in both these steps, you need to use the methyl bromide. If you want to prepare 1, 2, 3, 4, 5, 2-pentane, then in one step you need to take the methyl bromide, in another step you need to take the ethyl bromide. Okay. Now, what type of alkyl halides we can use and what type of alkyl halides we cannot use in the particular reactions, that we shall discuss now. We just see regarding the type of alkyl halides. It is preferable that use always primary alkyl halides. If you use the primary alkyl halides, then only you will be able to get the higher alkynes. If you use secondary or tertiary alkyl halides, then the molecule product will be alkene. So, what is the reason? The reason is, whenever the primary alkyl halide is used, then this particular alkynide part acts as a nucleophile. But when secondary and tertiary alkyl halides are used, this particular alkynide is acting as a base. So, I will show you those two steps here. So, straight away I will take the alkynide part. Okay. So, CH triple bond C minus, some Na plus is there. Now, let us take methyl bromide. So, it attacks over here, replaces this bromine, and we get the molecule like this. Now use the CH3 CH3 Br, secondary alkyl halide. So when secondary alkyl halide or tertiary alkyl halide is used, this particular negative charge preferably try to attack over the carbon attached to the halogen bearing carbon, next to the halogen bearing carbon. So here we can write the CH2 and hydrogen. So this alkyne part attacks over this particular hydrogen, and these electrons will be shifted between the carbon and this carbon, and bromine will be eliminated finally, so that HBr will be eliminated. So finally what molecule you are getting here? CH2 double bond CH and CH3, and here this hydrogen will be going and connected to this particular alkyne part. So as usually acetylene will means alkyne, original alkyne will be produced, and the sodium combines with the bromine and forms the NABr. What is the reason? What is the reason for this type of the attack? Why alkyne is attacking in one particular primary alkyl halides? In the case of the primary alkyl halides, it is attacking over the carbon to replace directly bromine. So it is attacking over the halogen bearing carbon. But in this case, second and tertiary alkyl halides, even you can take the tertiary alkyl halides also like this. So here also it attacks over the next hydrogen, and the molecule will be like this: CH3 C double bond CH2 and CH3 CH triple bond CH plus NABr. So let's try to know the reason behind this particular type of attack. In this particular case, halogen bearing carbon atom is more polarized. Why? Because here carbon atom is there. Even though if you add one more carbon atom this side, carbon halogen bond is more polarized than these particular cases. In this particular molecule, the halogen bearing carbon atom is connected to the two alkyl groups which are able to release the electrons through plus I effect, and here three alkyl groups are there which release electrons through plus I effect, so that this particular halogen bearing carbon, though there is a polarization, means halogen gets the partial negative charge and the carbon should get the partial positive charge. Here also partial negative charge, partial positive charge. Here also partial negative charge and partial positive charge. So in these cases, the positive charge over this carbon is less in these two cases. The reason is there are other groups which are releasing electrons to this particular carbon, so that the positive charge over this carbon is less. Hence, this negative charge preferably attacks over the next hydrogen, which can easily be removed because of the hyperconjugation, than attacking over these two carbon atoms. But in this particular case, if you are writing the R means here it will be CH2. So in this particular case, halogen bearing carbon atom is having the more positive charge. So this carbon finds more positive charge over the carbon, hence it directly attacks over the carbon to replace the bromine in the form of the Br minus ion. So that is the reason why whenever you are taking the primary alkyl halides, higher alkynes will be produced, and whenever you take the secondary alkyl halides or tertiary alkyl halides, the products are alkenes and alkynes, not the higher alkynes. Higher alkynes we cannot prepare. Now, here we have proved that this particular terminal alkynes are able to react with the sodium so that they are forming the sodium acetylide. Not only with the sodium, these terminal alkynes even they react with the other metals such as copper and silver also. So that first of all let us take the reaction with the copper molecules, means copper compounds or cuprous chloride. Formation of copper acetylide. So how these molecules will be prepared? Simply, when you take any terminal alkane. I will take only general example directly. You just take a terminal alkane that is having the triple bond CH. So when it is subjected with the ammonical cuprous chloride solution, Cu2 Cl2 plus NH4OH, usually here use the 2 molecules of ammonia, okay, because 2 chlorine atoms are there. So here ammonical cuprous chloride, the name of this one is ammonical cuprous chloride. So ammonical cuprous chloride on reaction with the terminal alkynes replaces this particular triple bonded carbon, hydrogen from the triple bonded carbon. So we get the R C triple bond C Cu. This is called the copper alkynide. Okay. So this copper alkynide also can be used in preparing the higher alkynes. But copper alkynide is in the case of the copper alkynides, carbon of the triple bonded carbon will have the less negative charge compared to the sodium alkynide. Hence, preferably the earlier compounds are used. This is if you take triple bonded acetylene with Cu2 Cl2 with 2 ammonium hydroxide, ammonical cuprous chloride, you will get the molecule like this, Cu and Cu. This is called the cuprous acetylide. This is a red precipitate. So this reaction also suggests that terminal alkynes are acidic in nature. Now, apart from this, one more test is there, that is reaction with the Tollens reagent. We might know that Tollens reagent. So, the compound is formation of, reaction name is formation of silver acetylide. Silver acetylide. We know that ammonical silver nitrate is called as Tollens reagent. So, we might have studied that carbonyl compounds, aldehydes, they react with the Tollens reagent. So, that is a test for the carbonyl compounds. But apart from the carbonyl compounds, even terminal alkynes also react with the Tollens reagent. So, you take the CH triple bond CH acetylene, when react with the 2 moles of AgNO3 in the presence of ammonium hydroxide, which is called the ammonical silver nitrate, so that they give the C triple bond C silver, and here it is a silver. So, it is called the silver acetylide, which is a white PPT, plus 2 moles of ammonium nitrate plus 2H2O. So, we can say that even terminal alkynes, not only this particular triple bonded acetylene, even RC triple bond CH also react with the Tollens reagent and gives its respective compound. But internal alkynes do not react with the Tollens reagent or any of these compounds. Then what is the use of these tests, both of these tests? These tests are very helpful in separating of the alkynes from the alkenes and alkynes, means particularly terminal alkynes from the other compounds. I will write down here. Note, both of these reaction means reaction with the ammonical Cu2 Cl2 and ammonical AgNO3 are helpful in separating the terminal alkynes from internal alkynes as well as alkenes as well as alkanes. So terminal alkynes react with both of these compounds so that they can easily be separated from the internal alkynes which do not react, alkenes which do not react, alkanes which do not react with these compounds. Then how can you get the alkyne back? It is simple thing that whatever the compounds so far we prepared just now, I'll take this molecule Cu, C triple bond C, Cu. So when this is subjected with the acid, you can take the any mineral acid like 2HCl. So copper react with the chlorine and hydrogen will go to the carbon so that we get the CH triple bond CH. Similarly, you take the silver compound Ag C triple bond C Ag. So again we react with the HNO3 or HCl. So HNO3 means Ag part react with the NO3 part so that we get the CH triple bond CH plus 2 Ag NO3 and in this case 2 CuCl. Both of this is a precipitate. And one more caution is these two compounds are explosive in nature. Means copper alkynides and silver alkynides both are explosive in nature. So when they become dry, they are very highly sensitive. So when they are dry, they explode. So that to explode very violently. So that is the reason why we have to handle these reactions. So these reactions and these compounds cannot be allowed to prepare in the laboratory, as these compounds, whenever they lose the moisture or whatever it may be, solvent, they immediately undergo explosion reaction. Thank you students. If you like the video, please like the video, share the video and comment whatever you feel about this video and subscribe the channel, and rest of the concept we will discuss in the next video.